Module 10, Lecture B, From Idea to Use. By the end of this lecture, you will be able to outline the main stages of a simple machine learning project lifecycle, relate each stage of the lifecycle to concepts learned earlier in the course, and explain why ongoing monitoring and revision are important after a model is first deployed. ML Project Lifecycle, defining the ML problem. A responsible machine learning project starts by clearly defining the problem before any coding or data collection. This means turning a vague goal, such as improving customer experience, into a specific decision or prediction the system will support, identifying who it will help and in what context. At this stage, you identify stakeholders, clarify business or social objectives, and decide whether machine learning is actually appropriate. For example, a hospital might narrow the goal of reducing readmissions to predicting which patients are likely to return within 30 days, so staff can provide targeted follow-up care. By the end of this phase, you should be able to state what input data you will use, what output you want, and how that output will fit into real-world decisions or workflows. When defining a machine learning problem, you must turn your plain language goal into a clear task a model can perform. Decide whether you are classifying categories, predicting a number, ranking items, or detecting patterns in data. Think about what each data example looks like, which features it includes, and what target outcome you want the model to produce. Finally, consider practical constraints, such as how fast predictions must be, how often the model will be updated, and what level of accuracy is acceptable. When defining a machine learning problem, you must consider ethical, legal, and practical constraints before building models. Check that your data is appropriate, representative, collected with consent, and that your predictions will not reinforce existing biases or cause harm. Whether a city is modeling building inspections or an employer is automating job screening, they must clearly define success, protect privacy, and keep humans involved in decisions. By addressing these issues early, you shape data collection, modeling choices, and evaluation so the system remains accurate, fair, and aligned with its goals. Building models from data. After defining the problem and gathering data, the next step is to build models that learn from historical examples to make predictions on new cases. You first prepare the data by cleaning errors, handling missing values, transforming raw records into meaningful features, and splitting the data into training and evaluation sets. For instance, in predicting hospital readmissions, you might turn patient records into features such as prior admissions or diagnoses. Once the data is ready, you select modeling approaches like linear models, decision trees, or neural networks, balancing interpretability, performance, and computational resources. Training a model means adjusting its internal settings so its predictions match patterns in your data as closely as possible. The model starts with a rough guess about how inputs relate to outputs. Then optimization methods gradually refine this guess by reducing errors. For instance, in credit scoring, the model learns that consistent on-time payments and stable employment signal lower risk, while missed payments and bankruptcies signal higher risk. During this process, you also choose hyperparameters that control how complex and flexible the model is, which affects both how well it fits the training data and how well it generalizes to new real-world data. Building models from data is an iterative process of trying different data representations, model types, and training settings to find what works best. Complex models can sometimes fit the training data very well, but fail on new data because they memorize noise instead of learning real patterns. In practice, a simpler model, such as one using past sales and seasonality in retail demand forecasting, may be more stable across different situations. Through experimentation and refinement, the goal is to find models that balance accuracy, robustness, and practicality so they are ready for formal evaluation and deployment. Python code building models from data. This script demonstrates how to build simple models using data, relying on very small synthetic datasets, so the ideas stay clear. The main goal is to show the overall process of training models and then evaluating how well they perform. Throughout, the emphasis is on doing this in a careful and responsible way, rather than on complex data or advanced techniques. We begin by importing 3 key libraries that support our data processing and modeling work. numpy is used for fast numerical operations on arrays and for performing mathematical calculations. Pandas provides tools to organize, manipulate, and analyze data in structured tables called data frames. Matplotlib's plotting tools allow us to create visualizations of our data and model results, helping us interpret performance and behavior. Together, these libraries form the core foundation of our workflow. We set a fixed random seed in numpy so that any random numbers generated by the script are always the same each time it runs. This makes the sequence of random values deterministic instead of changing from run to run. Having reproducible random numbers is important because it allows us to debug more easily and verify results consistently. In other words, using a deterministic seed helps ensure that experiments and analyses can be repeated and checked reliably. We begin by creating a small synthetic dataset for a regression problem. The dataset contains 30 data points. Using a numerical computing library, we generate feature values as evenly spaced numbers from 0 to 10. These values will serve as the input features for modeling a simple linear relationship. We begin by creating random noise from a normal distribution with a mean of 0 and a standard deviation of 1, matching the size of our dataset to simulate real-world variability. Then we define the target values by applying a simple linear rule to the feature, multiplying it by 2 and adding 3. Finally, we add the noise to these values so the data follows a clear linear pattern, but still includes some randomness, which is typical for regression problems. We place our generated data into a pandas data frame so we can organize it in a structured way. In this data frame, the feature values are stored together and the target values are stored alongside them. This arrangement makes the data easier to work with and analyze. Using pandas in this way lets us take advantage of its powerful tools for handling and exploring the data. We begin by checking the dataset's shape, meaning its number of rows and columns, to confirm it matches what we expect. We then use an assertion to verify that there are exactly 30 rows and 2 columns. This validation step is important to ensure the data structure is correct before performing any further analysis or operations. To prepare our data for modeling, we split it into training and testing subsets. We choose a training fraction of 70%, so most of the data is used to fit the model, while the remaining 30% is kept to evaluate its performance. We then find the size of the training set by multiplying the total number of data points by this fraction, and use that result to divide the dataset into the 2 parts. We begin by splitting the dataset into 2 parts, a training set and a testing set. Using simple index-based slicing, we take the first portion of the data as the training set, which serves as a representative sample for fitting the model. The remaining data, from the training cutoff to the end, becomes the testing set. This separation allows us to evaluate how well the trained model performs on data it has not seen before, helping to ensure it generalizes beyond the training examples. To prepare data for model training, we first take the feature values from the training dataset using the column that holds the input variable and convert them into a numerical array. We then do the same for the target values using the column that holds the outputs we want the model to predict. This separation into input features and target outputs is essential because it clearly defines what information the model learns from and what it is expected to predict. To prepare the training features for matrix operations in a linear model, we first create a column of ones the same length as the training data to represent the intercept term. We then combine this column with the actual feature values from the training inputs to form a two-dimensional array where each row represents one data point. After that, we transpose this array so that each feature, including the intercept, becomes its own column. This final structure allows us to use matrix multiplication to efficiently compute the regression parameters. To find the parameters in linear regression, we use the normal equation, which relies on two key matrix products. First, we multiply the transpose of the training feature matrix by the feature matrix itself. Then, we multiply the transpose of the feature matrix by the vector of training target values. These two results are then used together to solve the normal equation and obtain the parameters of the linear model. To find the parameters of our linear regression model, we slightly modify the normal equation by adding a very small regularization term to the main matrix. This is done by using an identity matrix scaled by a tiny value, which helps stabilize the computation. We then use a numerical linear algebra solver to compute the parameters from this adjusted equation. This regularized approach reduces numerical instability and helps guard against overfitting, especially when the dataset is small or the matrix is nearly singular. From the learned model parameters, we take the first value as the intercept and the second value as the slope. These two numbers are essential because together they define the straight line that best fits the training data. In other words, they capture the linear relationship the model has learned between the input and the output. We begin by taking the feature values from the test data, using the column that represents the input variable for our model. We then obtain the corresponding target values from the test data, using the column that contains the actual outcomes. These true outcomes are what we compare with the model's predictions to evaluate how well the model performs on the test set. To prepare the test features for prediction, we build a matrix where each row represents one data point. We first create an array of ones to serve as the bias term, and another array containing the test feature values. We then stack these arrays together and transpose the result so that the bias and each feature occupies separate columns. This final matrix has the correct shape for matrix multiplication during the prediction step. To make predictions on the test data, we multiply the test feature matrix by the model parameters we learned during training. This applies the linear model to each test example. Using the previously calculated intercept and slope, this operation produces the predicted target values for all points in the test set. To evaluate our model on the test data, we first find the errors by subtracting the predicted values from the actual target values. These errors show how far off each prediction is from the true value. We then square these errors and take their average, which gives us the mean squared error. This single number summarizes the average squared difference between predictions and actual values, and indicates how well the model performs on the test set. We begin by summarizing the dataset to confirm how many rows and columns it contains. We then report the sizes of the training and testing sets to show how the data is divided for building and evaluating the model. Next, we present the learned intercept and slope of the linear model, rounded for clarity, to describe its key parameters. Finally, we give the mean squared error on the test data, rounded to 3 decimal places, as a measure of how well the model predicts unseen values. We begin by creating a plotting area with a specified size to serve as the canvas for our visualization. On this canvas, we make a scatter plot where the feature values from our dataset are placed on the horizontal axis, and the target values are placed on the vertical axis. Each point on the plot represents one feature target pair from the synthetic data. We also assign a label to these points, called data points, so they can appear clearly in the legend. This scatter plot helps us visually examine how the feature and target values are distributed and how they relate to each other. To plot the regression line, we first create a set of evenly spaced x values between 0 and 10. Then we use the learned linear model to compute the matching y values by multiplying each x value by the slope and adding the intercept. These paired x and y values define the regression line, which we can plot to visually compare with the original data points. We plot the learned regression line on the graph to visually compare it with the data points. Using a plotting library, we draw a line based on the x values and the corresponding y values computed from the learned model parameters. This line is shown in red and labeled as the learned model, so it is clearly distinguished from the original data. We label the x and y axes of the plot to make it clear what the data represents. The x-axis is labeled as the feature x value, meaning it shows the input feature values. The y-axis is labeled as the target y value, meaning it shows the values we are trying to predict. These labels help listeners and viewers quickly understand the meaning of each axis and interpret the plot correctly. We add a title to the plot to show that this visualization is part of building a simple model from data, and to link it clearly to the overall project. This context helps viewers understand how the plot fits into the modeling process. We also include a legend that explains the different elements, such as the data points and the line representing the learned model. Together, the title and legend make the plot easier to read and interpret. To finish, we call the plotting library's show function to display the graph. This renders the data points together with the learned regression line. The resulting plot gives a clear visual summary of how well the model fits the data and the relationship it has captured between the input feature and the target variable. This script builds a simple linear regression model using synthetic data that follows a roughly linear pattern with added noise. The data is split into training and testing sets, with most of it used for training. The model's intercept and slope are computed using the normal equation, with a small regularization term added for numerical stability. After training, the script predicts values on the test set, calculates the mean squared error to measure performance, and prints the data sizes, learned parameters, and test error. It also plots the data points and the fitted regression line to show how well the model matches the underlying pattern. Model evaluation choices. Once you have trained your candidate models, you must carefully decide how to evaluate them, because this choice shapes all later decisions. Evaluation is not just about overall accuracy. It is about defining what good performance means for your specific problem. For example, a heart risk model should focus on catching as many true cases as possible, even if it raises some false alarms, while a loan approval model must avoid wrongly denying credit to qualified applicants. In practice, you decide which types of errors are more acceptable, and then choose evaluation measures that reflect those priorities. This keeps the technical work aligned with the original problem and the needs of the people affected by the model's decisions. To evaluate a model properly, you should split your data into separate training and testing sets so you can estimate how it will perform on future unseen data. The testing set acts like new real-world examples and helps reveal whether the model has truly learned patterns instead of just memorizing the training data. When data is limited, you can rotate which examples are used for training and testing to get a more stable estimate of performance. This separation helps avoid overestimating how good the model is and reduces the risk that strong development results will fail in real-world use. When evaluating models, you should look beyond accuracy and consider how they compare on values like fairness, interpretability, and robustness. A simpler model may be slightly less accurate, but easier to understand, maintain, and check for bias, which can be crucial in sensitive applications, such as hiring. It is also important to test how models perform when input data changes and across different groups, such as new versus returning customers. Overall, model evaluation is about managing trade-offs, so the model is not only mathematically strong, but also appropriate and responsible in real-world use. Python code, model evaluation choices. This script demonstrates basic choices in evaluating machine learning models. It compares two very small models on a simple artificial dataset. The goal is to highlight how overall accuracy can differ from the types of errors each model makes. By examining both accuracy and error patterns, we can better understand model performance. This script can be run immediately without installing anything new. All required libraries are already included in the current environment, so you do not need to add extra packages. As a result, you can execute the code smoothly with no additional setup or configuration steps. We begin by importing the numerical computing library, numpy. This library is important because it lets us work efficiently with arrays and perform fast mathematical operations. Using numpy is essential for the kinds of numerical tasks and computations we will carry out in this script. We set a fixed random seed in numpy so that any random operations in our code always produce the same results each time we run the script. This makes our experiments reproducible, meaning we can reliably repeat them and get identical outcomes. Reproducibility is important because it lets us verify results, compare different runs, and debug our code more effectively. We create a small synthetic dataset for a binary classification task, where each data point is a pair of feature values. The first two pairs with values around 0.1 and 0.2 represent low two-dimensional feature vectors. The next two pairs, with values around 0.8 and 0.9, represent higher feature values that may belong to a different class. This simple setup lets us test how well our models can distinguish between two classes based on these basic feature patterns. The code adds several more feature pairs to the synthetic dataset, including values like 0.15 with 0.18, 0.82 with 0.88, 0.4 with 0.3, and 0.7 with 0.6. These pairs expand the tiny dataset used for binary classification. Together, they help simulate a variety of simple scenarios that can be used to evaluate how well a model distinguishes between two classes. We use a numpy array to store the true class labels for each data point in the dataset. Each entry in this array is either 1 for a positive class or 0 for a negative class. These labels serve as the ground truth, allowing us to later compare and evaluate how well the model's predictions match the actual classes. Before moving on, the code verifies that the number of feature rows matches the number of labels. This check ensures that every set of input features has a corresponding label. By enforcing this one-to-one match, the code helps prevent data mismatches that could cause errors later in the process. We define a function to split data into training and testing sets by first computing the test set size as the total number of samples multiplied by the chosen test fraction. To avoid ending up with an empty test set, we make sure this size is at least 1 using a maximum operation. This approach lets us control how much data is reserved for testing, while still guaranteeing a meaningful evaluation of the model. The code uses a random permutation function to create a shuffled list of dataset indices. Because a fixed random seed was set earlier, this shuffling is random but reproducible. This randomized ordering is important for fairly splitting the data into training and testing sets, so the split does not depend on any original ordering in the dataset. The code takes the shuffled data indices and splits them into test and train groups. It assigns the first part, up to the chosen test size, to the test set, so that this subset is a random sample of the data. The remaining indices are used for the training set. This randomized split helps create balanced training and testing data, which is important for evaluating how well a model performs. This function outputs two groups of indices, one for training data and one for testing data. It first shuffles all available sample indices, then splits them into these two sets. Using these returned indices, you can divide the dataset into training and testing subsets. This split is essential for checking how well a model performs on data it has not seen before. We begin by using a helper function to create indices for the training and test sets. This function takes the total number of samples, which we get from the length of the labels array, and a fraction that specifies how much data to reserve for testing. In this case, we set the test size to 25% of the data. The function then returns one set of indices for training and another for testing, allowing us to split the dataset in a consistent and reproducible way for model evaluation. We build the training and testing datasets by selecting specific rows from the feature and label arrays using the train and test indices computed earlier. This process splits the original data into two separate subsets. One subset is used to train the model, and the other is reserved to evaluate how well the model performs. Properly separating these datasets is essential for getting a fair and reliable assessment of the model's accuracy. We build the test set by selecting the features and labels that correspond to the indices reserved for testing. This keeps the test data separate from the data used to train the model. By evaluating the model only on this unseen test set, we get performance metrics that better reflect how the model is likely to behave in real-world use. In this simple classification model, each data point receives a score by adding up all of its feature values. We then compare this score to a chosen threshold. If the score is greater than or equal to the threshold, we predict the positive class. If it is below the threshold, we predict the negative class. In this way, the model decides the class of each data point based on how its feature sum relates to the threshold. The code makes predictions by comparing each score to a chosen threshold. If a score is greater than or equal to this threshold, it is labeled as 1 to indicate the positive class. If it is below the threshold, it is labeled as 0 to indicate the negative class. This process is applied to every score in the dataset, and the results are stored as integers for clear and consistent predictions. The function outputs an array of predictions, giving a class label for each data point. It does this by comparing each computed score to a chosen threshold. If a score is at or above the threshold, the model predicts 1, meaning the positive class. If the score is below the threshold, it predicts 0, meaning the negative class. In this way, the model classifies data points based on how their feature sums compare to the threshold. This function computes confusion counts used to evaluate classification models, focusing here on true positives. It identifies true positives as the cases where both the predicted value and the actual value are 1. It then sums these matching cases and converts the result to an integer, giving the total number of true positive examples. This line computes the number of false positives by finding all cases where the true label is 0, meaning the actual class is negative, while the predicted label is 1, meaning the model predicted a positive, and adds up all such cases to get the total count of false positives. Finally, it converts this total into an integer to clearly represent it as a whole number. This line computes the number of false negatives in the predictions. It looks for cases where the true label indicates a positive class, but the model predicted a negative class. It uses a logical AND operation to identify these mismatches, then adds them up. Finally, it converts this sum to an integer to represent the total count of false negatives. This step calculates the number of true negatives in the model's predictions. It looks for cases where both the actual label and the predicted label are 0, meaning the model correctly identified a negative example. It then adds up all such cases to get the total count of true negatives and returns this count as an integer. This function returns 4 values that describe how a classification model's predictions compare to the true labels. True positives and true negatives are cases where the model correctly predicts the positive or negative class. False positives occur when the model predicts positive, but the true class is negative. And false negatives occur when it predicts negative, but the true class is actually positive. Together, these values show not only how often the model is right, but also what kinds of mistakes it makes, which is essential for evaluating its performance. We use a helper function to compute accuracy in a safe way by first checking that the true labels and predicted labels have the same shape. This shape check is important because any mismatch could cause incorrect results or runtime errors. By asserting that the shapes match before doing the calculation, we catch potential problems early and ensure the accuracy value we compute is valid. The code measures how many predictions are correct by directly comparing the true labels with the predicted labels. This comparison produces a series of true or false values, indicating where the prediction matches the actual label. It then adds up all the true values, which correspond to correct predictions. The final result is the total count of accurate predictions made by the model. This code measures how accurate a model's predictions are by comparing them to the true labels. It counts how many predictions are correct, then divides that number by the total number of predictions. The result is a floating point value that represents the proportion of correct predictions, which is the model's accuracy. Model A uses a threshold of 1.0 on the sum of feature values to decide whether a data point is classified as positive. Setting the threshold this low makes the model more likely to label cases as positive. This increases the chance of catching true positives, but also raises the number of false positives. Such a setting is chosen when missing a real positive is considered more costly than triggering extra false alarms. Model B uses a higher threshold of 1.5 to reduce false positives. With this stricter cutoff, it only predicts the positive class when the combined feature values are relatively high. As a result, the model becomes more conservative and produces fewer false alarms. This setup is preferred when the cost of false positives is high and precision is more important than recall. To evaluate Model A, we generate predictions on the test dataset using its threshold-based rule. For each test sample, we sum its feature values to produce a score. If this score is greater than or equal to Model A's threshold, we classify the sample as belonging to the positive class. Otherwise, it is negative. This procedure gives us a set of predicted labels for all test samples, which we then keep for later evaluation. We now generate predictions for the second model using the test data by applying the predict threshold function with the threshold chosen for Model B. For each test sample, the function adds up its feature values to produce a score. If this score is greater than or equal to the threshold, the model predicts a positive outcome. Otherwise, it predicts a negative outcome. This process allows us to see how well Model B performs with its specific threshold setting on the test set. The code evaluates the first model by computing confusion counts using the true labels from the test set and the model's predictions. This calculation produces the numbers of true positives, false negatives, and true negatives. These values form the confusion matrix and are essential for understanding how well the model is performing on the test data. To evaluate the second model, we use a confusion counts function that compares the true labels from the test set with the model's predictions. This function calculates how many predictions are true positives, false negatives, and true negatives. These counts summarize the different types of correct and incorrect decisions the model makes. They are essential for understanding the model's performance and the kinds of errors it produces. To find the accuracy of Model A, we use an accuracy scoring function that compares the model's predictions with the true labels from the test set. It first checks that both sets of labels have the same size, so they can be compared correctly. Then it counts how many predictions match the true labels, and divides this count by the total number of predictions. The resulting proportion represents Model A's accuracy and is stored as its accuracy value. To evaluate the second model, we use an accuracy score function that compares its predictions to the true labels from the test set. It first checks that both sets of labels have the same shape, so the comparison is valid. Then it counts how many predictions match the true labels, and divides this count by the total number of predictions. The resulting proportion is the model's accuracy, which is then stored as the accuracy value for the second model. We are breaking down the confusion counts for Model A to make the results easier to read and interpret. The tuple of metrics for this model contains true positives, false negatives, and true negatives. We assign each of these values to its own clearly named variable. This lets us refer to each metric directly by name, which makes the printed output and later discussion of the results more understandable. We now break down the confusion counts for the second model by assigning its true positives, false negatives, and true negatives to separate variables. This lets us clearly label each type of correct and incorrect prediction. Organizing the metrics this way is important for later analysis and comparison of the model's performance. It makes it easier to discuss its accuracy and the kinds of errors it makes. This part of the script prints a short introduction explaining that it is comparing two simple models using a separate test data set. The message sets the stage for the results by making clear that the goal is to evaluate how well the models perform on data they have not seen before. This context helps the listener interpret the performance numbers that follow as a fair test of generalization. We report the accuracy of Model A, which is designed to maximize recall. To do this, we display the accuracy value using a formatted message that rounds it to 3 decimal places. This gives a clear, concise summary of how well the model correctly identifies positive cases. The rounded accuracy makes the performance easy to read and compare. We report the accuracy of Model B, which uses a higher decision threshold to focus on precision. The accuracy is rounded to 3 decimal places to keep the output clear and easy to read. This metric shows how well Model B correctly identifies positive cases while reducing the number of false positives. We examine the confusion matrix for Model A, which reports the numbers of true positives, false negatives, and true negatives. These values show how often the model correctly identifies positive cases and how often it makes mistakes, such as labeling negative cases as positive. Looking at this breakdown helps us understand the specific types of errors the model makes. This information is essential for evaluating the model's performance beyond overall accuracy and for revealing its strengths and weaknesses in different error categories. The code prints the confusion matrix from Model B, showing how many predictions are true positives, false negatives, and true negatives. By examining these counts, you can see what kinds of mistakes the model makes. This information is essential for judging how well the model performs and for deciding how to improve it. The final line of the script reminds us that choosing a decision threshold should depend on which types of mistakes matter most for the specific problem. It highlights that model evaluation is not only about overall accuracy. Instead, we must think carefully about whether false positives or false negatives are more acceptable or more harmful in the given application. This focus on the consequences of different errors guides how we set thresholds and judge model performance. This script shows how to evaluate and compare two simple binary classification models on a small synthetic dataset. It creates data with numpy, splits it into training and testing sets, and makes predictions by summing feature values and comparing them to different thresholds. Model A uses a lower threshold to favor recall, while Model B uses a higher threshold to favor precision. For each model, the script computes the confusion matrix values, including true and false positives and negatives, as well as overall accuracy. The printed results highlight how changing the threshold shifts the balance between recall and precision, and the script emphasizes that the best threshold depends on which types of errors matter most in a given application. Linking core concepts. Connecting features and targets. When moving from abstract models to real projects, it is crucial to distinguish between features and the target. Features are the input data the model uses, and the target is the outcome it tries to predict or classify. For example, in predicting hospital readmissions, age and medical history are features, while whether a patient is readmitted within 30 days is the target. Correctly identifying these elements connects theory to practical machine learning design, and getting them wrong can undermine the entire project. In a project lifecycle, linking features and targets begins by clearly defining the problem and understanding the data. You first decide what decision or prediction you want to support, which becomes your target. Then you identify what reliable information you have to help make that prediction, which becomes your candidate features. For example, a city transport department predicting bus delays might use time of day and weather as features, with delay in minutes as the target. This process turns the abstract idea of inputs and outputs into concrete data collection and labeling, making sure the target matches real-world goals. The relationship between features and targets in a project has both ethical and practical consequences at every stage. Features come from historical data that may contain collection biases, and targets are based on value judgments about what counts as success. For example, a hiring tool that predicts high performers using past performance ratings can reinforce existing bias if those ratings were unfair. Features that indirectly capture socioeconomic or demographic information can also harm certain groups. Revisiting how features and targets are defined throughout the project helps ensure that both inputs and outcomes are fair, reminding us that technical choices are also ethical decisions. Training and evaluation. During the training phase of a machine learning project, the model learns by adjusting its internal parameters to reduce prediction errors. The data is split, so the model can be trained and then evaluated on separate sets. And a loss function measures how far its predictions are from the correct answers. An optimization method, often based on gradients, uses this loss to update the parameters and gradually improve performance. You can think of it as an ongoing negotiation where the model proposes predictions, the loss function judges them, and the optimizer refines the model so it generalizes better, such as learning to recognize disease patterns in medical images by comparing its outputs to known diagnoses. To evaluate a model, you reserve part of your data as validation and test sets, and may also use cross-validation to see how well it handles new examples. You then measure performance with metrics such as accuracy and precision. Comparing these results across training, validation, and test data helps you spot problems like overfitting, where the model does well on training data but poorly on new data. By examining different data splits and metrics, you judge not only how well the model works, but also how it might fail in real-world use. Training and evaluation are closely tied to bias, variance, and fairness in machine learning models. Simple models can have high bias and miss important patterns, while overly complex models can have high variance and overfit the training data. Techniques like regularization and careful model selection help balance these issues. During evaluation, fairness metrics are essential because a model may look accurate overall, but still perform poorly for certain groups. Together, training and evaluation aim to ensure the model meets technical, ethical, and societal standards. Python code, training, and evaluation. This script demonstrates basic training and evaluation steps using a tiny synthetic dataset for a simple regression task. Its main purpose is to show how these stages fit together in practice, rather than to build a complex or realistic model. As you follow it, focus on how the training and evaluation lifecycle connects back to the core concepts you have already learned. To use third-party libraries such as numpy in Python, you usually install them with a package manager. In most cases, you use a tool called pip to add numpy to your environment. Doing this makes sure the library is properly installed and available for numerical computations in your Python programs. We begin by importing the numpy library, which is designed for efficient work with numerical data. This tool lets us create and manipulate arrays and perform mathematical operations quickly. By bringing numpy into our script at the start, we prepare the environment for all the data handling and calculations that follow. We use a fixed random seed in the numpy random number generator, for example the value 42, to make our results reproducible. This means that every time the script runs, it produces the same sequence of random numbers. Having consistent random output is important for debugging and for checking that the code behaves the same way across different runs. We begin by generating synthetic feature data using a function that creates evenly spaced numbers over a chosen range. In this case, we produce 20 values between 0 and 10. We then reshape these values into a column vector so that each row represents one data point and the single column represents the feature. This format is convenient for many machine learning methods that expect data organized by rows and columns. To create the target values for our synthetic dataset, we start with the feature values, multiply them by 2 to represent the slope, and then add 1 to represent the intercept. Next, we add random noise generated from a normal distribution with mean 0 and standard deviation 1, using the same number of values as in our features. This noise introduces natural variation, so the targets follow a simple linear pattern but are not perfectly exact. The result is a more realistic dataset suitable for training a regression model. Before splitting data into training and test sets, the code first checks that the number of feature samples matches the number of target samples. This step confirms that every feature entry has a corresponding target value. Ensuring this one-to-one match is essential for keeping the data consistent and reliable during the split process. We create a split index by taking 70% of the total number of data points in our feature array. This index is used to divide the data into a training set and a test set. As a result, 70% of the data is used to train the model, and the remaining 30% is kept for testing. This separation allows us to evaluate how well the model performs on data it has not seen during training. We create a training subset by slicing the full feature array from the beginning up to the split index. This means we only keep the first portion of the data for training. That subset is then used to fit the model so it can learn patterns from that part of the dataset. In other words, we are separating out the data the model will learn from. We now take a slice of the target values array to create the training subset, using all values up to the previously defined split index. This subset provides the portion of the data the model will learn from. By training only on this part, We can later test the model on the remaining unseen target values. This separation is essential for fairly evaluating how well the model generalizes to new data. We create a test subset by slicing the array from the split index to the end. This subset is kept separate from the training data. Later, we use it to evaluate how well the model performs on data it has not seen before. This helps us judge how well the model generalizes beyond the training set. We take the remaining part of the target values, starting from the split index to the end of the array, and use it as the test labels. This is part of dividing the dataset into training and test sets. The test labels are kept separate so we can later evaluate how well the model performs on data it has not seen during training. We begin by initializing the parameter of our linear model, the weight that defines the slope of the line, to 0. This 0 value is a standard starting point in linear regression and serves as a neutral baseline. With no initial bias toward any direction, the model can then adjust the weight purely based on the training data. This setup allows the learning process to shape the slope according to the patterns it finds. We begin by setting the bias term, which is the intercept of the linear model, to 0. This gives the model a neutral starting point with no initial offset. During training, the model will adjust this bias value based on the data, so it can better fit the relationship it is trying to learn. We set the learning rate to 0.01, which controls how much the model parameters change at each step of gradient descent. A smaller learning rate makes smaller updates, leading to more stable but slower convergence. Because of this trade-off, choosing an appropriate learning rate is crucial for effective training. The code sets the number of training epochs to 200, meaning the training loop runs 200 times. In each pass, the model updates its parameters to reduce the loss function. This number of epochs is chosen to give the model enough chances to learn from the data, while helping to avoid both underfitting and overfitting. We define a helper function that computes the mean squared error between true values and predicted values. It does this by taking the difference between each true and predicted value, squaring those differences, and then averaging them. The final result is a single floating point number that represents how closely the predictions match the actual values, with smaller values indicating better predictions. During training, a loop runs for a set number of epochs to perform gradient descent on the training data. In each pass through the loop, the model computes predictions using the current linear parameters. It multiplies the weight by the training features and then adds the bias. These operations produce the predicted values for the training data at that stage of learning. The code computes the difference between the model's predicted values on the training data and the actual target values, and stores this difference as the error. This error measures how far the predictions are from the true values. It is a crucial quantity because it is then used to calculate the gradients that guide how the model parameters should be updated during training. To compute the gradient for the weight in a linear model, we take the error, which is the difference between the predicted and actual values, and multiply it by the corresponding feature values from the training data. We then average these products across all training examples. This average value is the gradient, and it indicates how the weight should be adjusted to reduce prediction error. By following this gradient, we move the weight in the direction that minimizes the overall error. The code computes the gradient for the bias term in a linear model by averaging the errors over all training examples. Each error is the difference between the model's prediction and the actual target value. This mean error is then multiplied by 2 to scale the gradient. Finally, the result is converted to a floating point number to maintain precision in later calculations. In this step of gradient descent, the weight is updated by subtracting the learning rate multiplied by the gradient of the weight. This means we adjust the weight in the direction that most reduces the error. By repeatedly applying this update, the algorithm moves the weight toward an optimal value that minimizes the overall error. In this step of gradient descent, the bias term is updated by subtracting the learning rate multiplied by the gradient of the bias. This operation slightly reduces the bias in the direction that lowers the training loss. By repeatedly applying this update, along with similar updates to other parameters, the model gradually improves its fit to the training data. After training the model, we use the learned weight and bias to generate predictions on the training data. For each example, we multiply the weight by its feature value and then add the bias. This calculation produces the final predicted values for the training set and shows how well the model fits the data it was trained on. To make predictions on the test data, we use the learned parameters of the linear model. For each test example, we multiply its feature values by the learned weights and then add the learned bias. This calculation produces predicted target values for all test points. We can then use these predictions to assess how well the model generalizes to new, unseen data. We use the mean squared error on the training data to evaluate how well the model fits that data. A helper function takes the true target values and the model's final predictions, then computes the average of the squared differences between them. This single value summarizes how close the predictions are to the actual training targets and serves as a measure of the model's accuracy on the training set. To evaluate how well a model generalizes to new unseen data, we calculate the mean squared error on the test set. This measure uses the true test values and the model's predicted values, then computes the average of the squared differences between them. The result is a single number that summarizes the model's performance on the test data. A lower mean squared error indicates better accuracy and reliability when the model is applied to new data. The code prints the version of the numpy library being used and the learned weight and bias of the linear model. This gives a quick overview of both the computing environment and the outcome of training. By checking this output, you can confirm which numpy version is running and see the final values of the model parameters after the training process is complete. The code reports the mean squared error for both the training and test data, rounding each value to 3 decimal places to keep the results clear and readable. By comparing these two errors, you can see how well the model fits the data it was trained on and how well it performs on new, unseen data. This comparison provides a quick view of the model's overall performance and its ability to generalize. This line prints a short summary of the model's training and evaluation results. It explains that a lower training loss means the model fits the training data well, while the test loss shows how well it generalizes to new, unseen data. Understanding this difference helps you judge whether the model is only memorizing the training set or can also perform well on new examples. In other words, it helps you balance fitting the known data with achieving good performance on future data. This script walks through a simple linear regression example using synthetic data with a noisy linear relationship. The data is split into training and test sets, and a basic linear model with weight and bias starting at 0 is trained using gradient descent to minimize mean squared error over many passes through the data. After training, the script reports the version of the numerical library used, the learned weight and bias, and the mean squared error on both the training and test sets. The training error shows how well the model fits the data it learned from, while the test error indicates how well it generalizes to new, unseen data. Better data, better models. When we say better data leads to better models, we mean that data quality, sampling, and bias directly shape how a model behaves. A model can only learn from the data it sees, so if that data is limited, unrepresentative or biased, the model will inherit those problems. For example, a model trained on data from just one hospital with a narrow patient group may not predict surgical complications well for other populations. Because data collection often reflects social and institutional biases, improving the data is essential for building models that are both accurate and responsible. Improving data quality is not just about correcting mistakes or filling in missing values. It requires careful choices about what you measure and how you measure it, while making sure diverse experiences are represented. If a hiring algorithm is trained on past biased decisions, those biases will be built into the model. To address this, you can redefine the target you are predicting, collect more relevant information, and intentionally include more data from underrepresented groups. These steps build on earlier ideas about turning abstract concepts into measurable variables and recognizing the social context in which data is created. Better data is essential for building fair and accountable models. Even if a system appears fair according to standard metrics, it can still fail in real use if the underlying data is unbalanced or misses important groups, such as gig workers in a credit model. To address this, teams must continually revisit how data is collected, work with affected communities to find gaps, and question existing assumptions. This ongoing improvement of datasets is key to better model performance, fairness, and trustworthiness over the entire lifecycle of a data-driven system. Monitoring deployed models, adapting to data shifts. When a model is deployed, the data it sees often changes over time, which is called data shift. Because the model's learned patterns are tied to past conditions, its predictions can become less accurate as real-world situations evolve. For example, a model that predicts public transport demand may fail if a pandemic or a new transit line changes how people travel. If we do not monitor and update the model, it will keep relying on outdated patterns, leading to poor decisions, reduced service quality, and loss of public trust. Machine learning models must adapt because the data and context they operate in can change over time. For example, a health chatbot trained on younger users may perform poorly if older adults start using it, since the input patterns shift. Likewise, changes in regulations or economic conditions can alter what counts as ethical or reasonable decisions, such as a credit scoring model trained before an economic downturn, misjudging risk when unemployment rises. Without regular updates, models can become inaccurate, biased, or irrelevant, harming both performance and ethical standards. Adapting to data shifts requires more than occasional retraining. It needs a planned strategy to detect changes and choose responses that protect users and stakeholders. This can include regularly updating training data with recent examples, validating models before deployment, or designing systems that learn incrementally while staying stable. For example, an educational recommendation system should use user feedback without overemphasizing popular content, so it preserves diverse learning options. By planning for adaptation, documenting updates, and involving experts and communities, models can remain aligned with current data and ethical standards and avoid degrading as conditions change. Spotting performance drift. Performance drift occurs when a model's effectiveness slowly declines, making its predictions less accurate or less fair over time. This change can be subtle and dangerous, such as a credit scoring model that once predicted loan defaults well, but becomes unreliable as economic conditions or customer behavior shift. Without careful monitoring, the model may keep producing decisions that look reasonable but are systematically wrong, harming both the organization and the people affected. Detecting performance drift is therefore essential to maintain quality and trust in automated systems, and to prevent unnoticed degradation in systems that impact real lives and resources. To detect performance drift, compare how the model behaves now with how it performed when it was first deployed. Regularly track key metrics such as accuracy and error rates over time. and examine them across different user groups or case types. For example, a medical triage model might become less accurate as disease patterns or patient demographics change, leading to issues like under-triaging certain patients. By consistently checking current metrics against historical data, teams can spot these gaps early and address them before they cause serious problems. Performance drift is not only about changes in accuracy, it can also appear in shifting error patterns, fairness issues, or business impact. A system might keep its main metric like click-through rate or prediction quality stable while quietly reducing content diversity or disadvantaging certain groups or regions. Because these shifts may not show up in a single number, teams need to track multiple dimensions of performance to stay aligned with current goals and ethical standards. Training people to notice these subtle forms of drift helps them update models early and explain any changes clearly to stakeholders. Scheduled model checkups. Scheduled model checkups are like routine health exams for deployed systems, done at regular intervals such as weekly or monthly to confirm everything is working as intended. At each checkup, you systematically review the model's performance, inputs and outputs against clear criteria. For example, in a university admissions model, you might compare predicted student success with actual outcomes and look for demographic biases in past decisions. Making these evaluations a regular practice helps catch subtle problems early and reduces the risk of major failures over time. To make model checkups effective, use a consistent, predefined process instead of improvising each time. Decide in advance which metrics, datasets, and questions you will use, and apply them regularly. For example, you might track default rates by risk band in a credit model, or have clinicians and data scientists jointly review recent triage cases in a hospital model. By following the same protocol over time, you can detect trends such as declining accuracy or growing disparities, rather than treating each review as an isolated event. Regular scheduled model checkups help guide decisions about maintenance, retraining, and governance. By reviewing performance with stakeholders, you can plan updates, document what changed, and clearly inform users. Organizations may time retraining around key events, such as a retailer preparing for a busy season, or a city updating traffic models when routes change. These routine reviews keep the model aligned with shifting user needs and overall organizational goals. In this lecture, you learn to outline the main stages of a simple machine learning project lifecycle, relate each stage of the lifecycle to concepts learned earlier in the course, and explain why ongoing monitoring and revision are important after a model is first deployed. Congratulations on completing this course.
Thank you for your attention. See you all in the next lecture.